Hey, EP Statistics. So in this section, we are going to look at exponential models and how we can fit data that have an exponential curve like this, y equals a times b to the x, where it could be some base, it could be 2 to the x or 3 to the x, and it's growing exponentially, or it could be 1/2 to the x, and it's exponential decay. So a scatter plot of the logarithm of y against x should produce a roughly linear relationship. So we don't take the log of both, just the log of y against x. And so y is that. So if we take our exponential and we go ahead and take the logarithm of both sides, and so these should still be equal, this relationship should still be true. But we'll see if we follow our log rules here. So we can split this up into log a plus log b to the x, and then we can bring that x out front. And so what we end up here is a linear relationship between x, log b is just a constant, so b would be whatever your base is. So x times that plus this constant, and so we actually end up with times a constant plus a constant equals log y. So x and log y follow a linear relationship. And that's if that thing originally was exponential. So, for example, in this case, Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. Here are data on the dates and number of transistors for Intel microprocessors. Here is a scatter plot that shows the growth in the number of transistors on a computer chip from 1971 to 2016. Notice that we used years since 1970 as the explanatory variable. We'll explain this later, but if Moore's law is correct, then an exponential model should describe the relationship between the variables. So they left out the data, but here they plotted it for us. Years since 1970 and number of transistors in billions. And the reason we do this is just actually to make the numbers much more reasonable. Otherwise, if you go and actually do it as years since like the year 0, you end up needing to have a really precise value to begin with. So this ends up being much nicer for working with this. All right, so here's a scatter plot of the natural base. They took log base e, logarithm, of the number of transistors on a computer chip versus years since 1970. Based on this graph, explain why it would be reasonable to use an exponential model and describe the relationship between the number of transistors and years since 1970. So when we took years since 1970 and they took the logarithm of the number of transistors, and we see it looked pretty linear. So the scatter plot of the natural log of transistors versus years since 1970 has a fairly linear pattern, so an exponential model seems reasonable here. So for part B, here is some computer output from the linear regression analysis of the transform data. Give the equation of the least squares regression line. Be sure to define any variables you use. So we've got our slope and y-intercept, that nice strong relationship, but this is between x and log y. And so we will do this y-intercept plus slope times x, which is years since 1970, is equal to the logarithm of our transistors. And of course, it's the predicted number. And so then the last bit they asked us to do is use that equation we just came up with to predict the number of transistors in 2020. All right, so we plug in 50 years since 1970. So that's why we plug in 50, multiply, add, get a number. The natural log of transistors equals that. So then we can convert that to exponential form. So it's base e, so e to the 24.9 is equal to the predicted number of transistors, which is a lot. 67 billion. So this model predicts that an Intel chip made in 2020 will have about 68 billion transistors. So it turns out that this rate did not end up coming true. This prediction ended up being accurate. We're doing a lot of extrapolation, and so things did slow down a bit since then. Suppose that a scatter plot shows a curved relationship between two quantitative variables, x and y. How can we decide whether a power model or an exponential model better describes the relationship? So the following example shows the strategy we should use. So we've got some data here. On July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. They had first observed this object almost 2 years earlier using a telescope at Caltech's Palomar Observatory in California. Originally named UB313, the potential planet is bigger than Pluto and has an average distance of about 6.3 billion miles from the sun. For reference, Earth is about 93 million miles from the sun. Could this new astronomical body, now called Eris, be a new planet? At the time of the discovery, there were 9 known planets in our solar system. Here are data on the distance from the sun and period of revolution of those planets, along with the scatter plot. They left out the data, but they got the graph here. Note that distance is measured in astronomical units, the number of Earth distances the object is from the sun. There appears to be a strong curved relationship between distance from the sun and period of revolution. So rather than measuring millions of miles, that number is really big, we did astronomical units, which is just the Earth distance from the sun. And so at 1 is where Earth would be. So you got a few closer, a few further, and so on. And then we've got the period, the number of years for revolution. And so we're going to take a couple of cracks at it. Basically, the following graphs show the results of 2 different transformations of the data. The graph on the left plots the natural logarithm of period against distance from the sun for all 9 planets. So log versus just regular distance, so kind of seeing if it's exponential. The graph on the right plots the natural logarithm period against the natural logarithm of distance. So we took 2 natural logarithms, and there it is, nice straight relationship. So this is definitely appears to be a power model. So based on the scatter plots, would an exponential model or a power model provide a better description of the relationship between distance from the sun? Justify your answer. So the log of both is much more linear than the graph of log of period versus distance, so a power model would be more appropriate. So here's the computer output from a linear regression analysis of the transformed data in the graph on the right. Give the equation of the least squares regression line. Be sure to define any variables you use. So in that case, we used the logarithm of both. So log x, which in this case distance, logarithm of the period is the y value. You get your slope or y-intercept and slope. So you plug those in, y-intercept and slope, times that logarithm of distance. And then finally, use your model to make a prediction for Eris, which is about 68 astronomical units away. We plug in 68.05, take the logarithm, natural logarithm, multiply, add, we get that number. So that's logarithm base e of period. So we do, this is wrong. This should be 10 to that power, but we get that predicted 561 years. All right, sorry, it should be e to that power, not 10 to the. Here is a residual plot for the linear regression in part B. Do you expect your prediction in part C to be too large, too small, or about right? Justify your answer. So we do actually see there is a little bit of curve. And so if our distance is our natural log of our distance is 4.22, which would fall at the far right of the residual plot where the residuals are positive. And so because it's likely that the residual actual minus predicted is greater than 0, we would expect our prediction to be too small. The actual would be higher. Our prediction is too small in that case. So it seems like that curve wasn't the perfect fit, but it's definitely a lot better than exponential. And then you can just kind of search through this, just a couple of types of curves that we'll deal with.